Hello everyone. Today I would like to show you how you can use OrthoSAM within a Google CoLab framework. I'm going to use a free version of Google CoLab, which has limited computing resources. And with that, we are also only able to process smaller sized images. I'm going to use an example from SediNet because these images are easy to access and of good quality, and they are relatively small so that we can use Google CoLab for that. The size limit is approximately 2000 by 2000 pixels, so roughly 4 megapixels. If you are going to use 24 megapixels, you will not be able to use that within the Google CoLab framework, and you either need to, within the free Google CoLab framework, you either need to purchase computing resources or you need to use a local hardware resource that I'm going to show you or already showed you in the other videos. So we are going to start out by setting the appropriate hardware acceleration. So edit notebook settings. The T4 GPU is the hardware accelerator that is available for the free version. If you are paying for computing resources, you may be able to access other GPUs, and those additional GPUs will also allow you to process large orthomosaics, as we have done in the accompanying manuscript. So I already went ahead and did the first couple of steps to speed up that video here. So I'm installing my repo, the GitHub repository. We are cloning it, and from that cloned repository, we are going to install the requirements. That takes about 2 minutes. And next, we are going to download the pre-trained model from the MetaSAM repository. That high-resolution pre-trained repository or pre-trained model that we are going to use is roughly 2.4 gigabytes large, and that is going to be placed in a very specific subfolder where OrthoSAM can find it. We are only using the high-resolution pre-trained model because this is what is most appropriate for Pebble grain size delineation. Next, we are updating the directory and the config files. This can be automatically by changing into the directory where the data are being stored and processed. That is content OrthoSAM on Google CoLab, and then we are running our update config.py. Next, we are going to get the image that we are going to segment. We are first creating a directory, and I am getting the image from this GitHub webpage. So if we look at this GitHub webpage, this is Daniel's photo. This is a nice image of a dense Pebble collection. And we are going to download this image, and you are placing it into the SediNet folder. You have to do that step manually. Next, we can start the OrthoSAM instance. So we are changing in the code directory. We are importing all required utilities, and we are going to set up the parameters. So this is a step where I would like to spend a few minutes on explaining them. So the way OrthoSAM works is that you have a list of multiple parameters, and these parameters are being passed to OrthoSAM, and the processing is being started. What we are doing here in the main parameter list, we are defining the output directory. This is the output directory, and this is a SediNet output. And the way this is being done is that we are saving a separate file or separate directory for every image that is in the folder. Right now, we only have one image in our input SediNet folder, so we are just producing one output folder. With ID equals 0, we control which file we are going to process in the input folder. So our purpose of this somewhat more complex parameter setting is that we can have many photos, individual photos in one directory and process them all in one step. So that's why we are using the ID to identify which photo we are going to process. And since there is only one photo in there, it's going to be ID equals 0. If we are setting this to none, then we would process every photo that is in that subfolder. So let's leave it at 0 because that's our first image. And that is also our file ID. The example image doesn't have any meaningful resolution. Usually when you create an OrthoSAM, you know the resolution of the file because you have done the scaling. So right now we are setting it to 1, keeping it in mind that this is more or less an arbitrary unit that we are seeing here. We are using the maximum tile size of 1024, and we are assuming an overlap of 200 pixels on that 1024 tile. I'm going to demonstrate this in a little bit how we can change that. We are using the original resolution. So if you have a very, very high resolution image, you can already do a downsampling or resampling step here. But generally speaking, it's useful to use the original resolution in the first iteration that you are doing. We are creating 30 by 30 input points. These are the seed points or the starting points of where OrthoSAM is trying to segment out the segments. These are some filtering steps that we are not going to talk about in detail now. The step that may be important is to set the expected minimum size. OrthoSAM or MetaSAM has a limit on the has a size detection limit that lies roughly at 30 pixels. Here we are saying we would like to throw out all sizes, all pixel sizes that are less than 50 pixels. I'm using the term pixels now because we have arbitrarily scaled this resolution to 1. If you are using a properly scaled OrthoSAM, then you would have the proper unit to put here. We are calculating stats, the statistics as the output. We are going to do a small analysis with this, and we are not doing a Discord notification. This is only useful if you're doing a long processing chain where then you would receive a message when the processing is done, and we are doing some plotting. So this is the main parameter list. This is a parameter list that identifies the first layer, the initial layer. This parameter list defines the additional parameters that are being employed at the second iteration or at the layer 1 if you want. So this is layer 0, this is layer 1. And the only parameter that we are changing is that we are saying in the second iteration, we would like to resample by a factor of 1/2 or 0.5. And that's also the reason why I'm calling that output directory up2, because that means I'm upsampling by a factor of 2. So I'm reducing the resolution, having the x-axis and the y-axis pixel sizes to do a second run. And this is usually useful to identify the coarser pebbles in an image. We also have some pre-processing parameters that we are not using for this example. So you could do an initial Gaussian smoothing, or you could do a normalization of your image, a histogram normalization in a specific neighborhood. You could do some resampling or buffering, such as cropping. We are not doing any of those pre-processing steps. That is likely more useful if you have a large number of photos that you would like to process and apply some kind of a homogenization filtering step. So we can look at those parameters. This is just giving us the output of that parameter list. We can then make sure that we have created all output images, and we can do our that we created all output directories to store the data. And then we can do a first simple plot using our parameters to see how the tiling would look like on our image. So the command plot tiling with overlap shows us the image as a background. So this is roughly 1500 by 2000 pixels, and it shows us the tiles. So this tile here is the first 1024 by 1024 tile, and then we have a 200 pixel buffer overlap, and this is our next tile that we are generating. So this is then the second tile. Altogether we have 1, 2, 3, 4, 5, 6 tiles. So we are tiling our roughly 2000 by 1500 pixel image into 6 tiles, and each tile is separately being fed into OrthoSAM. The reason that I'm stressing that fact here with a buffer is that the buffer needs to ensure that no pebble that is within the buffer is exceeding the buffer size. So we are seeing that those pebbles are generally smaller than the buffer size. If you have a much smaller grain size in order to speed up processing, you can change the overlap, let's say, to 100 pixels. So if we are recreating that parameter list, and we are replotting our original image with the overlapping buffer, then we see we have now created a much smaller buffer. I'm not very happy with this buffer because it would not include the pebbles. So that means that I feel more comfortable with a larger buffer. Let's go back to our original 200 pixel buffer, and that then allows us to have a save option. If you have a larger grain size, you likely would increase our buffer. So what OrthoSAM is doing, OrthoSAM is expecting a parameter list, the parameters that we just set, and that is being stored in a JSON file. So there is a parameter list saved as a JSON and a pre-processing parameter list. We are currently not applying any pre-processing, so we don't need to worry about this. But then that parameter list is being passed into OrthoSAM. I pre-run this. The segmentation for that single image takes roughly 6 minutes on the free Google CoLab instance, and I'm just going to talk through the results here. But this list is what is being passed to OrthoSAM, and then either all images or all different parameters are being applied. The reason for that is that the reason why we decided to do it that way is that you first can refine your overlap, for example, or other parameters before putting it into a long run that then can be done in a remote machine as well. So let's look at the results. I'm scrolling up here. When you run this in a Jupyter Lab on your local machine, you will see many more output patterns that is being suppressed here in the Google CoLab output, and we are just seeing the images that we are plotting. So this is layer 0, meaning this is the first layer that we have done. And this is our RGB image. We have identified initially 487 masks, and this is then the segmentation that has occurred. So this is already including some of the filtering step. So this is the second layer that you see here. The second layer, or layer 1, because you start counting as 0, is a resampled layer of a factor of 0.5. So we identified fewer segments. This is 487, this is 344. And then we are going to merge those layers. So there are many duplicates that were identified in both layers, and we are only merging the layers that that were not identified in the first image. So, for example, you see here is a pebble missing and maybe here is a pebble missing. They were not identified in the first run, but they were identified in the second run, and these are then being merged. So what OrthoSAM is telling you at the output is then the difference in the pebbles that are being added. So these are the pebbles that are being added to create the second final layer. So those parts that were missed in the first run are being added in the second run. So you can already see that there are some shapes in here that don't necessarily refine pebbles. These are essentially the pebbles that are below or under a pebble above. But this and this one looks like a true pebble. So we now have a merged layer that we can analyze further, and this is something that we are going to do in the next step. Before I go there, I would like to point out what are the resources that have been used here. So I'm going to go to my view resource pattern. I'm going to look at how much we have used processing that in that image. So we had used about roughly half of the available system RAM and more than half of the GPU RAM at its peak. So if you're using a larger image, either the system RAM or the GPU RAM will be exceeded and the processing stopped. So this was my earlier comment pointing out that the free version of Google CoLab may not be appropriate for large OrthoSAMs unless you purchase computing resources. Okay, so let's look at some simple results, and I'm stressing the fact that this is not a publication-ready analysis that I'm doing here. I'm just pointing out what you can do with those segments and the statistics that we are calculating. We are going to load in the file, the property file that is essentially a CSV file, and we are going to read it in with pandas. So this is being stored in our output SediNet, and here we have the props.csv or properties.csv. We are going to load this in, and we are going to look at the first couple of lines of that pandas data frame. So we have the centroid coordinates, and we have our AB or the major and minor length axis. We have an area, perimeter. We have parameters that describe the roundness. This is the isoperimetric ratio. And we have parameters or columns that describe the mean color, red, green, blue, and the median color. So those last 6 columns can be used for doing a lithology classification, for example, feeding it into a random forest classifier, but explaining that is beyond the scope of this little video. Instead, what I'm going to do is I'm going to do some simple visualization and filtering steps. So we have a total of 493 pebbles in there. We can do a simple statistics. So our mean size, our mean major and minor size, for example, would be shown here as a simple statistics that exists. So we can plot the sizes. So this is a scatter plot using the centroid location, the X and the Y centroid location, and we are choosing the colors to represent the A-axis, and the size of each pebble is actually scaled by the area. So the units here would be millimeters if you would have used an appropriate unit in your parameter file. Let me scroll back here. So the resolution we now set arbitrarily to 1 for this example, because Google CoLab is not able to work with higher resolution images, and I didn't have another example, so I used an example that did not have a proper scaling, and therefore these units that you are seeing here are not the true units. These are essential pixels, but you will have your own image that is definitely properly scaled. So let's load in the label and see if we can combine that with our first results here. And I'm going to load in the label. This is an NPY layer. So this is our NumPy layer. We are loading in the highest number layer because that's the final merged layer. So if we look into merged, in the subdirectory in the output folder, we have the first iteration and the second iteration, and the second iteration is always the one that also contains the merged version from the first one. So we are using the layer 001. If you would have had additional layers, then we would need to load in, for example, 002 or so. So we are converting that integer NumPy array into a floating array just so that I can set the background to NaN, because that's easier for visualization. I'm just doing that for visualization purposes. And here is our number of labels that we have in here. So let's display this, and I'm going to display this by merging it with our centroids. So I'm using a random color scale using grayscale values. I'm plotting our merged labels, and I'm plotting on top of it our scatter plot, again showing the color scale to be the axis major length, and I'm now forcing all points to be the same size. And you can see that this is our output. We have the centroid nicely identified, but we also see that some pebbles, for example, this one or this one here, or maybe this one or this one, they are no real pebbles. They are essentially the pebbles that are below 2 pebbles on the surface. So we may want to think about removing those pebbles, and that will be the next step that I'm going through. So I'm showing you a very, very simple way of removing segments that may not be pebbles. You can, of course, always do that manually, but there are some semi-automatic approaches that will allow you to filter your segmented mask to produce a more realistic pebble label dataset. And we are going to use the roundness metrics, the isoperimetric ratio. There is a lot of research that was done with pebble shapes and how they can be measured, and I'm just referring to a couple of papers here, but the literature body is much larger than what I'm pointing out here. I'm just simply taking and building upon these earlier studies to use the isoperimetric ratio, which is a roundness definition, and it's the ratio of the area in 2D to its perimeter. Because that area in 2 dimensions, such as this image here on the array, is influenced by the shape, or that ratio is influenced by the shape, we are going to use a normalized factor, and this is the IRN, so the normalized isoperimetric ratio. We can plot the isoperimetric ratio for all of our pebbles, and we see that many of the pebbles are on the order of 0.8, 0.9, so the colors are orangey, yellowish. So these are the well-rounded pebbles that we also see in the original RGB image. However, we have a few pebbles that are very unrounded. They are down here at 0.4. And what we are going to do is we are going to use a very simple threshold. So this is not a meaningful threshold in that sense. I'm just saying I would like to look at all of the pebbles that are less than 0.5, that have a roundness factor of 0.5. I'm getting my roundness, or I'm getting the pebbles that are less than 0.5, so I'm just saying less than 0.49 here. This is the list of pebbles that are not very round. And I can then create a new data set and create a new label data set that only points out those pebbles that are not really round. So let's look at this. These pebbles are here, and you can see that some of those are the shapes of the overlaying, this is the remnant segment of the overlaying pebbles that can safely be removed. Here, for example, is one segment has two images in it. So this is something where we then can do some additional filtering and editing on it. But in the general sense, we would use the normalized isoperimetric ratio to remove pebbles that are no true pebbles. So let's do this. When we plot this again, now we are plotting in color the isoperimetric ratios less than 0.5 in color, and in grayscale are all the other pebbles. So we probably could play around with that threshold a little more and or add a manual delineation step, but we definitely get rid of some of the pebble artifacts that are not true pebbles. As a last step, I just would like to show that we can use the pandas framework or the props.csv to perform a very simple size distribution plot. So here I'm choosing only the pebbles with a isoperimetric ratio above 0.5. So this gives me 480 pebbles. And then I'm using a very simple pandas plotting function. You probably would like to use a more sophisticated matplotlib function to plot the graph in a more visually appealing way, but I'm using 20 bins. I'm using a log scale, a true y-axis. I'm plotting a cumulative plot, and I'm showing you the minor axis length, so that's the b-axis, and the a-axis distribution. So this is something that can then be further evaluated. However, keep in mind that this is a relatively small data set and that we have not properly scaled this data set with an arbitrary scaling. So this is why the size is shown here as pixel. So this was a very short video introduction to using OrthoSAM on the Google CoLab framework, and I'm hoping that this was useful for you. Thank you for listening.